In this video, we will talk about the Monte Carlo method. Monte Carlo method is a simulation of the underlying process. It uses the repeated sampling to obtain simulated results. So here is a graph of Monte Carlo simulation, and I have put 50 passes here. If we look at the end of the paragraph, here we can see that most stock price concentrated around the center, and that is the initial stock price multiplied by the expected return. I use the expected return of 1% here. But there are also some outliers that is way above or way below the expected stock price. That is because the stock price also have volatilities, so some of them will deviate from the expected value. If we have large enough samples, we will have a final simulation that will closely match the analytic distribution. So we can use the simulation to calculate the option payoff and then discount it back to the initial point. So we will have an estimation of the underlying of the option. So that's basically how Monte Carlo works. For Monte Carlo method, we will also use the Black-Scholes-Merton process, and we need some other parameters. We will talk about them on the Quantlib website. The Monte Carlo pricing engine is also under the vanilla option engines, and we will use the Monte Carlo European engine. So here is the constructor, and we'll also copy and paste it to our Word file. The first parameter in the Monte Carlo European engine is the generalized Black-Scholes process. Fortunately, we already have this process in the last video, so we will skip it this time. And the second one is time steps. As we know that Monte Carlo, the Black-Scholes-Merton process is a path-dependent process. So if we use different time steps, we will have different results. So we will use time steps of 10 here. And next is time steps per year. We will use just a null here because we don't specify the time steps per year. And next two is Brownian motion and anticyclic variate. Both of those two parameters are used so that you can have reduced computational effort. Those are also our methods that seeks to reduce the computation effort without reducing the accuracy, but we will not use them here. So those two are bool values, and we will set them to false. The required samples is the number of samples that we use in the simulation. Here we will use 10,000 samples so that we will have an acceptable estimation without too much computational effort. The second one is required tolerance. As we all know, the Monte Carlo method is just a simulation of the final result, so it will inevitably have some deviation from the real value. The required tolerance specifies the maximum deviation that you are willing to take. And the max samples is usually used together with the required tolerance. The larger the sample is, the lower the tolerance will be. However, if the program chooses to use a very large sample, it will take a very long time for the computer to calculate the final value. So the max samples will set a limit of the samples that we use. The last parameter is seed. We would like the program to generate pure random numbers for us, but in fact, let's just generate pseudo-random numbers. If we start with the same seed value, we will have a particular sequence of random numbers, so that each time we run the program, we will have exactly the same result. Here we will use a random seed generator to generate different seeds every time we run the program, so we will have slightly different results every time. You can specify the seed yourself. The seed is a big natural type, which is just large positive integrals. So if you specify a particular seed, every time you run the program, you will have exactly the same numbers. So now we have gone through all the parameters of the Monte Carlo European engine. Now let's go to the coding part. So we will write the Monte Carlo method based on the previous program we wrote in the last video. because in that program we already have the option and the Black-Scholes-Merton process, both of which we will still need to use in this program. First, let's define some parameters that is specifically required in the Monte Carlo method. So the generalized Black-Scholes process is already defined, and then we have the time steps, that is 10. And the next one is the time steps per year. We will not need this parameter here. So we will define it as null. Next one is the Brownian bridge and the antistatic variate. As we said, both will be set to false. And the required samples will be 10,000. The required tolerance and max samples will not be used here. The last one is the seed. We will not give a specific seed number, but will use the seed generator to generate a seed each time we run the program. So now we have all the parameters ready, we can start to build our Monte Carlo pricing engine. First, let's open the Quantlib. You can see here that after the Monte Carlo European engine, we have two other parameters in the angle brackets after the name. Those are random number generator and S. If we go to the end of this page, we can see that the random number generator will be pseudo-random as we described earlier, and the S represents statistics, so we will put those two parameters in our code too. So now let's start to build the Monte Carlo engine. Now we will pass all the parameters to the function. The first one is generalized Black-Scholes process. We already defined that, the BSM process. The next one is time steps, that is defined here. And next, time steps per year. And next, Brownian bridge. And then the antiseptic variate. And required samples. And required tolerance. Max samples. And last, seed. So now the Monte Carlo engine is already built. We will try to output the results. Now let's build the solution and run the program. Because the Monte Carlo method requires more computational efforts, it might take some while. So the core price estimate from the Monte Carlo method is quite close to that from the analytic method. If your result is deviated from this result, don't worry, because the Monte Carlo method will generate different results every time. But it should not have a very large deviation, since we have 10,000 examples, so we expect the deviation to be not so large.